Thank you, Mr. Chairman. Okay, so I'll give some insights on why and how microwave chemical vapor infiltration can achieve optimal fabrication, and it's this results from the modeling work package, which is basically an understanding work package. So, I'm from Laboratory for ThermoStructural Composites, which accumulates something like 36 years of research and innovation on CMCs. It's a joint lab of CNRS, University of Bordeaux, to which I belong, and also with the Safran group through Safran Ceramics, and from the CEA, which is the French Atomic Energy Agency. Oh, that's something that has changed. Well, the activities of LCTS are along 4 axes. One is processing, the other one is really characterization of structural and chemical composition. The third one is to test the behavior at any scale and in any combination of mechanical, thermal, and chemical loads. And the final one is multi-scale modeling. This is the one I was wishing to circle. I don't know why it changed, but I'm quite worried for the rest of the presentation. Okay, and the activity that we've been carrying out in the CEM-WAVE project was principally about multi-scale modeling of the process. I also wish to introduce the French National Research Group on Ceramic-matrix Composites, characterization, modeling, conception, which is CMC Square, and we have a regular series of workshops. By the way, Stefan, you are going to give another talk in one of these workshops in January. And well, the French research group joins companies like these ones here, large or small companies, but also, of course, research entities and also agencies, including Army or nuclear waste disposal. Okay, so CVI is something that we already have been describing. So the main point is that your precursor gases, well, for example, hydrocarbons to create carbon, are introduced in that furnace with usually low enough pressure so that it can diffuse easily between the fibers here, and by heterogeneous reaction lead to solid deposit and also the evolution of byproduct gases. Okay, so that's fine, but the problem is that isothermal infiltration leads to premature pore plugging. And the idea is that we should activate the chemical deposition rate in the end of the pore and not at the pore mouth. So how to do that? Of course, the idea is to apply a thermal gradient, hot inside, cold outside. So if you do so, you have heat going from one side to the other, so thermal gradient. And the idea is that, of course, the chemical reaction is active in the hot part. Then the precursor gas makes more or less the opposite way. And this results in a dense zone here, and you're shifting everything in the direction of more precursor gases entering the material. And variations of CVI, including thermal gradients, are numerous, and there's a long literature on that, dating back to the 80s or to the 90s. So, for example, you can heat by contact with a hot susceptor. You can also have an electrical current directly going through the material, especially when you have carbon fibers, which are conductive. You can also use radio frequency heating on these same carbon fibers, or you can use microwaves, and it's in that class of processes that we are here. You can also have a boiling precursor outside of the preform in order to ensure that you have a very cold side, so a very strong gradient. In the 90s, Oak Ridge had developed something with a pressure gradient in addition to the thermal gradient to force the gases through the preform. And I also have been working on this supercritical high-pressure infiltration, which was also involving thermal gradients. So literature is really full of variations of thermal gradient. And microwave CVI is only one of these modalities. But there are some principles that are common to all of them. So let's focus on microwave CVI now. Okay? The starting point of modeling and understanding this affair is the deposition reaction. Locally, in any point of your preform, the deposition reaction relies on three parameters. The internal surface area, which is a function of porosity, the rate law here, which depends on temperature through Arrhenius laws, and the gas precursor concentration here. So if you do so, you need three variables at least to describe the reaction zone. So this gives you some ideas of multiphysics coupling, because densification is the equation here for the evolution of porosity. Heat transfer here is for the evolution of temperature, and diffusion reaction is for the evolution of the reactant. Okay, so we got three of them. But of course, heat transfer is also a combination of heat consumption, heat losses, and heat input, which comes, in our case, from electromagnetism. So this gives the fourth block of this multiphysics coupling. And the difficulty of modeling that is that everybody depends on everybody. So we are all bundled together. And especially through the dielectric properties, the thermal properties, the diffusion, gas diffusion properties, the kinetics, well, many things. These are the effective properties that we have to compute here. So in the CEM-WAVE project, we propose a two-scale computational strategy. The first one was more focused on getting these effective properties, which depends on porosity, also on temperature, and also on the initial state of the preform. And the second block here is macro-scale computation that would be more linked to understanding how it works at the preform, at the whole part scale, okay? And this one is more on the coupled multiphysics, with, of course, the effective properties being transmitted from one to the other. So multiscale in practice is, for example, here we received, after a certain time, some samples from, in particular from Fraunhofer, and these are the oxide, and the 6-ic preforms. Okay, so we could get some micrographs of the fibers and also some tomographs of the layup morphology. And we made some image processing in order to retrieve exactly where the fibers were. Okay, so then after that, we changed that with a meshing procedure using a distance from the interface here in order to optimize density of elements. Actually, in this region, for example, you are far away from the interfaces, so you don't need to have such a tight mesh. So we are gaining some time and some memory effort by doing that trick here. Then, computing the effective property computation. I'm sorry for the formulae. The idea is that you don't want to compute the actual temperature under a given applied gradient in a given small bit of the material, because you would have to repeat that forever in many situations. So to be more general, you take what's called a closure variable, which is the proportionality between the temperature perturbation which is actually the difference between the actual temperature and the average temperature, compared to the magnitude of the average thermal gradient applied to the material. If you got a strong average gradient, then you have strong perturbations. If you have a small average gradient, then your perturbation is small, okay? And the beauty of the maths of that is that you can, and I don't show you how, obtain the effective property tensor out of the averaging of the local property with a variable, with that closure variable here. And from that, we can get what you want, that is, transmit only one tensorial property to the next scale, okay? This is an example of computing the closure variable field here, but we had a problem, which is a usual problem in the community of homogenizing or getting effective properties, which is, well, these images are not periodic, whereas the assumptions for all these mathematical developments were made with the idea that the material is similar everywhere. And usually, I think out of laziness, people are just assuming a periodic medium, a periodic unit cell. But the problem is that our images are not periodic at all. So we worked out a specific numerical method to address the fact that they are not periodic. And, well, to our surprise, it worked. So we just figured out, how is it possible that nobody thought about that in 40 years of homogenization? The result, that's an example of a result. You got for lots of degree of pore filling, infiltration. Also, what's not shown here is the initial volume, fiber volume fraction in many images is different. And then the temperature, so you can have an idea of the fact that here the property diminishes with increasing temperature. So we got lots of data. This is for the best eigenvalue, the other eigenvalue here. And then the problem is that this depends on too many parameters, and it's difficult or impossible to have correct analytical formulae interpolating the properties from all those, correlating to the fiber volume fraction, to the matrix volume fraction, temperature. So we tried out and found that random forest regression algorithm, which is one of the classical machine learning algorithms, was the best one to save our day. And we optimized the number of estimators here. And the result is that the machine learning algorithm shows a much superior performance by correlating really very well the prediction to the actual value that's estimated, as compared to what, well, analytical regressions would be doing. So that's one of the recent outcomes of the project. Now, we also have then inserted all those effective properties and their evolution in something which is a large-scale material physics model, which was then run to reproduce the data presented by Roberto in the preceding talk with the flat plate. But we also made an analytical study, and we could understand how you could tweak the parameters in order to optimize your process. So this is the experiment that has been shown. So this is currently, by the way, submitted to a journal. And what we only chose to do was to select the hottest point of the surface and just look at what's through the thickness here. So it was only necessary to take a 1D model here through the thickness, in which we have basically assigned a trapped standing wave inside the material, so that we could figure more or less what a heating power distributions could be, even if it's not really very realistic. I'm sorry for that, Giuseppe. And then we had the thermal equation. We had, of course, the infiltration equation. I forgot to put the concentration equation here, We also simulated the regulation, thermal regulation, so that the assigned power was always such as the surface temperature never moved from the set point temperature. Okay? And these are the results. So we have the value of porosity at selected points through the thickness. So this is the surface, and you see that the porosity at the surface diminishes, but slower than porosity in the middle, so which is exactly what we want. And this is, for example, a final porosity profile here showing that indeed in that situation, with all the data that we had gathered from many steps before, we came to the point of having exactly the inside-out gradient. And surprise, using kinetics from literature, we found also agreement on the time scales, which was rather surprising, because in chemical kinetics, if you are 2 orders of magnitudes away, you are sometimes very close to the result. Okay, so why was it so good? It's because here gas diffusion was not limiting. The benefit of the inside-out gradient was therefore very well exploited. But let's have a look at the criteria based on the dimensionless number to understand that better. And the dimensionless numbers are 2 here. One is the Thiele modulus, which takes the length of through the thickness dimension here, and then you got the surface area and the hottest chemical rate constant here divided by the diffusion of the gas. So it's the diffusion reaction competition. And if that length is too large, of course, it means that you are depleting completely your reactant inside your preform. And the other one is the Zeldovich number, which is the relative thermal difference amplified by the activation energy. And one has to look at the fact that the activation energy is something that amplifies the importance of a thermal gradient, okay? And, well, in that space, we have shown that 4 types of situations can occur. Well, the classical ICVI or isothermal CVI situation is there, in which you simply have a premature crusting of your preform. When one criterion is met, it means that the faster the reaction rate is faster inside, but crusting ends up occurring. And this is what I call the Trilby hat effect, okay? Because you have a profile like this. And the second criterion here is that what we want is that really the distribution of the reaction rate does not display an extremum inside inside the material. And the last criterion is the existence of an infiltration front, which is simply a standing wave that goes from the inside to the outside and infiltrating nicely the whole material at its best efficiency. So, in the case that we have modeled, we were okay. Not so far from the border, by the way. We computed the Thiele modulus, the gradient parameter, and it was okay. And now, what does occur when you have an increase of thickness? If you increase the thickness, then you move up in this diagram, and you are moving to the region in which one of the criteria is not met anymore. So, indeed, in the detailed modeling, you have a crossing of the lines here, indicating that you will have a Trilby hat effect. And it's even worse if you triple the thickness, evidently. This is what you can see here, because this one is the density in the center, which is much less decreasing than the one at the surface. So, but if we double the thickness, we can try doing something to recover the correct situation. And the simplest way of doing that is lowering the temperature. In that case, by 50 Kelvin, you lower the temperature and you can compensate. If you triple the thickness, then you have to lower even more the temperature. The problem is that, of course, things are getting slower because, well, 100 Kelvin means like 5 times slower. Well, we can collect all that in a temperature thickness space here, for example, in which you have a dividing line between the existence of a front or the non-existence of a front, or the correct situation and the undesired situation. And, well, here what we see is that the actual experiment is on the good side, and if you increase the thickness, you can rapidly enter the domain of inefficient infiltration, okay? And, okay, this is what we are wishing to now compare to as many practical situations as possible, because these conclusions are, well, general in some way, but they depend, of course, on the details of exactly the preform properties. And every time you change a bit your preform, for example, you have tighter fibers, then, well, the properties are not exactly the same. Then, well, it shifts a bit away the situation. But in principle, we have here all the tools that allow an engineer to guide himself through the jungle of the parameters set and find a possibly correct situation, and not by chance, just in that case with some educated guesses. So the main points of this work is that, MWCVI requires multiscale and multiphysics modeling, as we could see, because of the multiscale nature of the material and also the multiphysics nature of the process. So an image-based modeling suite has been created. It incorporates original techniques with machine learning in the end to exploit at best the resulting correlations. The multiphysics large-scale computations were validated with respect to experiments, which is a very strong point, and I hope that the European Commission officer will be happy with that. And an analytical study matches the detailed computations so that guidelines for optimizations are really delivered. And well, I thank you for your attention, and I'm open to any question.
Questions for Professor Vignoles?
I have a question. So could you, let's say, envision, let's say, in situ measurement, let's say that you have in situ measurement of the, let's say, gradient, or say like something like porosity inside, and then let's say you tweak your model, and that you can then also tweak the parameters of your infiltration, let's say. I mean, like let's see. So you have your model. You have the in situ measurement of properties inside, and then let's say adjust your process accordingly. Could that be like something to envision?
Well, to answer, as you know, a model is like an integrated circuit with lots of input ports, output ports, and ports that can be reverted between input and output. So you can use the modeling frame back and forth. You can use it for identification of the missing properties or the missing information, for example. So that's one point. But the other point is that we have evidently tried to build something out of only input and not getting the output to obtain a simulation of the output, which becomes more trivial. So we paid lots of time to obtain and retrieve from literature independent data on the fibers property, on the interface property, on the matrix property. We also paid attention to obtain detailed structural information on the fiber arrangement and the fiber volume fraction. That is really what comes from well, at least one of the preforms that the Fraunhofer Zentrum had given us. Okay? And yeah, out of that, we guessed correlations of properties, okay? And we inputted that in a global scale model in which we tried to be as faithful as possible, as honest as possible with respect to what was the real experimental conditions, in particular simulating this constant outside temperature regulation, which is the way they are running the process. And well, of course, it's not perfect, but at least we do not we are on the right side of the diagram, which is one of the important points here. Especially when you see all the bricks that we have been piling up together without back-checking or doing anything special for just getting it stronger, okay? So this is already one very good point of confidence, and evidently you can now like improve every bit of the whole set and also have some other independent checks. For example, we have now fresh data on the evolution of thermal conductivity at several stages of infiltration. We, at the beginning, had only guessed from the knowledge of the usual properties, the known properties of a silicon carbide matrix, and what we know on the fibers, that the evolution would be this one, okay? And now we have actual data on that. So, well, for the forthcoming weeks and months, even though the project is over, we are going to like go backwards and show that, well, the modeling is not saying anything completely out of realism. Okay? Does that answer enough your question?
Hello? So earlier on, well, it's known that the decomposition of MTS to form silicon carbide is quite dependent on the temperature. And Roberto showed earlier on that you get, he is able to deposit quite carbon-rich silicon carbide, possibly as a result of the lower temperatures. But do you think that having a thermal gradient inside your CMC will mean it's challenging to get stoichiometric silicon carbide deposits?
Well, that's a very good question, because actually we have been hiding lots of things here. Well, you know, most of the people, when they start modeling this from a chemical engineering point of view, they start with the simplest situation possible, which is only assuming a single reaction with first-order kinetics. Okay? That's the first thing you have to do, and then you say, okay, well, this is not always true, but well, later you can make your constant, your rate constant vary on some composition or whatever. We were very happy to see that we had a good match with the time scales immediately without doing any any tweaking specifically. That was quite surprising. On the other hand, what we see here is that we were in a very good situation due to the fact that you had a very slow chemical reaction as compared to transport, okay? So slow chemical reaction, no great perturbation of the gas phase by the deposition reaction. So in that case, indeed, a simple linearization is probably not totally out of tune. But we know that if you play with, for example, the gas phase composition with the hydrogen to MTS ratio, if you play with temperature and you go to higher temperatures, well, nothing is granted anymore. And you may have changes in the reaction rates. It changes even in the stoichiometry of deposits in my lab. When I was still a student, there were colleagues of mine doing their PhDs together with me before 92, 93, and they had established that, well, with the same system, you could switch from silicon excess to carbon excess, passing through stoichiometric silicon carbide, just by playing with temperature and the hydrogen to MTS ratio, and also with the global pressure. So, yeah, in practice, all this data should be like gathered, collected, and inserted in the model in order to try and have it extend its realm of action, okay? Does that answer your question?
Yes, it does. Thank you.
Okay. Let's thank again our speaker.